All right, it is time to start. It is now 1 p.m. UTC, 6 a.m. for me. Welcome to 6MAN. This is our second session at IETF 108. Today we have the agenda up. We have first to talk about working group draft, the minimum path MTU option, and then we have talks on 3 new individual drafts, and we will try to manage the time to get through all of this. And so there's not any questions, we will start. So I think Anna was going to present. Or Torlis, did you comment?
Submissions that are, as time permitting. So I was wondering how that came about.
We've done that for the last couple of years because they're new working group drafts. I mean, today I think we will get through the time, but we've always done that for give lower priority to new drafts that haven't had a lot of discussion.
But so you're saying you had them when you were planning for the time?
Yes, but if the working group drafts run over,
okay,
then we won't guarantee the new drafts get time.
No, sure. Thank you.
Okay. Okay, Anna, go ahead.
Hi, everyone. Can you hear me?
I can hear you.
Perfect. I won't be sending video today because my DSL line is literally in a tree at the moment. And hopefully you will run the slides and I will tell you when to play next.
Yes, we will.
Perfect. I think the first 2 slides are... Oh, you skipped the title slide, I see. Perfect. Well, to introduce myself, I'm Anna. I work with Gori Fairhurst at the University of Aberdeen. We do internet measurements. And today I'm going to talk a bit about some experiments that we did with extension headers and what we learned from them, all in the context of the minimum path MTU hop-by-hop option draft. So if you go on to the next slide, I can tell you all about our probes that we did. Can we go to slide 2?
So I see you on slide 2 or 3?
I would love to go to slide 2.
Oh, that's 2. Okay, you have the wrong order on the PDF. That's fine.
Oh, right. That's not ideal. But okay, so we have a need to do a lot of non-standard measurements that have to do with setting packet bits or using different types of headers like IPv6 extension headers. And often we try to do this from as many vantage points as we can. For this, we use small single board computers like the ones you see in the pictures. They're APU boards. So these are our probes. They run Linux. They're configured as a fleet with Ansible. And we currently have 4 of them. One is at the University of Aberdeen, and then we have another 3 that are hosted by some very kind people, some of which hopefully are listening. And they're in various places. We have one in the Janet Slough Data Center in the UK, and this one is hosted by Team Chon. And then we have 2 others in California, one hosted by Bob and one hosted by Warren Kumari. We are definitely interested in deploying more and run more experiments from more places. So if you want to host one of these, get in touch with me or Gori, and I will also have some more details at the end of the presentation as well. So we use these probes to run IPv6 extension header experiments. And if we go on to the next slide, or rather 2 slides onwards, to slide number 3, I will tell you all about them. Yes, perfect. So specifically, we did tests with hop-by-hop options and with destination options. We did 2 types of tests. end-to-end traversal tests where we send DNS queries to 20,000 name servers and we look for DNS responses. And we also did trace route style tests where we send ICMP messages starting with a hop limit of 1 and increasing it each round, and then we record replies from routers on the path. Each and every measurement, we start by sending a vanilla packet that has no extension header, and this provides us with a control measurements that we can then compare against. So for each target, this means we test 3 times, once with a vanilla packet, and once with a hop-by-hop option header, and once with a destination option header. So if we go on to the next slide. Here I tell you what goes in the extension header. Well, for the end-to-end versal tests, we tried different things. We tried to send a valid pad n option, which just sends 4 bytes of padding. This is a well-known option that routers on the path understand, and this is why we wanted to test it. We then tried to send an invalid pad n option as well to see if that makes it. By invalid, I mean it says it sends 8 bytes of padding, but in fact it only sends 4. We also tried to send all zeros, and then finally we also tried to send an unknown option, which is the minimum path MTU hop-by-hop option that is proposed in Bob and Gory's internet draft, just to survey any barriers to deployment to it. So if we move on to the next slide, before we dive into the results, I will basically just try to categorize what happens when you send a packet with an option, or with an extension header rather. So you either get a reply from the destination. In our case, for the end-to-end traversal tests, this would be a DNS response. And then you consider the traversal successful. Or the packet can be silently dropped, either by the destination or somewhere along the path. And then next, please. When the packet is dropped, then whatever drops it can also send back an ICMP unreachable message. That would quote the packet as it was received at the hop that dropped it. But I'm going to talk about the first case here, the case where we actually got an answer to our DNS query. So if we go on to the next slide, I will give you traversal numbers on the next slide. But for now, just to sum up what we learned. So we found that 50% of the DNS servers we tested will actually reply to a query that comes in an IPv6 packet with a destination option header. This was actually true regardless of where we tested from. So from every single vantage point, we got a similar consistent result. The story is not so great for hop-by-hop options, where it seems to depend drastically on the vantage point. For example, no packets with a hop-by-hop option header received a response because they never made it outside of the Comcast network, well, in the case of Bob's probe, so from Bob's house. We did not look at other home access networks, but we plan to. Well, what we also found is that an invalid pad n option, the one that advertises a different length than the one it sends, does not actually traverse the path at all. So from this, we can actually conclude that routers actually look at the header and parse it along the path. And if they see something wrong with it, they drop the packet. I also mentioned testing with the minimum path MTU option. So the good news is that while it is an unknown option, it has a very similar traversal rate to that of a pad n option, which is well known. So the routers who forward options will forward the packet anyway, even if it has an option that is not known. So now to look at the numbers, we can go on to the next slide. Okay, so here you have traversal numbers for hop-by-hop destination options from February and July. So I guess here you can see how we get consistent results for destination options, but not hop-by-hop options. Just like I presented in the previous slide, we can see that not much has changed between February and July. And we can also see that a lot of packets with options actually get dropped. So the next step was to look at where this happens in the network. And if we go on to the next slide, I will move on to talking about the results that we got from the tracer style measurements. Now, so These measurements are done by sending ICMP packets with increasing hop limit values. And if a router can't decrement the hop limit and forward the packet, then it sends us back an ICMP hop limit exceeded in transit packet. This quotes the original packet as it arrived at the router. This means that for each measurement, we can look at whether or not the packet was altered. And what we found is that nothing changes, nothing along the path seems to change the pattern option we sent. So the routers on the path did not tamper and modify the extension header. However, we did find one hop that completely removes the extension header, as in removes it entirely. And this IP address seems to belong to Information and Computing Technology Services for Tertiary Institutions in Hong Kong. It must be some sort of packet normalizer box. But yes, this is a case and this happened. Now, another thing to note is that when sending these packets, I make a note of the hop limit that the packet was initially sent with and encode this in the ICMP payload of the packet so that we're able to extract it when the packet is quoted back to us from routers on the path. So I guess for each measurement, the largest hop limit that is returned to us essentially tells us how many hops the packet made it along a path before it was discarded. So for every single measurement, we made a note of the number of hops each packet traversed, and we averaged them. And this is something we can see on the next slide. And here we can see actually how a vanilla ICMP packet compares to a packet with either a destination option or a hop-by-hop option header. So surprisingly, it looks like packets with destination options actually make it almost as far into the path as packets without any extension header at all. We see the number are very, very similar for the control probe that we sent and for the destination options probe that we sent. So this tells us that the drop actually happens very close to the destination or even at the destination, in the destination AS in any case. So while destination option packets are probably discarded at the server edge, hop-by-hop options seem to be discarded a couple of hops earlier. But surprisingly, they also still have a chance of making it quite far along a path before being dropped. So and the average here was 14 hops before being dropped or either receiving a reply. You see here the results from one vantage point, which is from Aberdeen, but this was actually the case for every other site, well, apart from Bob's house, where the average number of hops that a packet with hop-by-hop options traverses is around 3 because the packets never make it out of the Comcast network. Right, so if you move on to the next slide, I can tell you all about what we learned so far. Well, the packets with options travel quite far across the internet paths we looked at. However, we didn't measure many access networks, and we need more info here. We'd like to measure more of those. We also only tested DNS, so we only tested UDP and ICMP. We did not test TCP, but so we don't know if there's a difference, but this is also something to keep in mind and look at later. When the packets are forwarded, in some cases, up to 42%, they reach the destination and they can be used by an algorithm such as the DPLP-MTUD one. But in most cases, they are actually silently dropped. And because of this high drop rate, we probably options should be sent on standalone probe packets rather than on packets that would impact the flow in case they were lost. This relates to how some firewalls are configured by default. So, for example, you have PF, which is the default firewall for OpenBSD, and also it forms part of FreeBSD as well. And there are many commercial firewalls that are based on these. And PF, for example, drops packets with some extension headers by default, and you have to enable them to let them through. So does IPFW, which is the main firewall in FreeBSD, but it only does this with unknown options. But also, I mentioned earlier how when a packet is dropped, it can send back an ICMP unreachable message, and that would give us some sort of insight into what happened to the option along the path, and if it could record a partial value that we can maybe use for an algorithm. However, most firewalls actually will not give you back an ICMP unreachable message. And it's not just the case for IPFW MPF. I'm guessing this is probably the case for many more firewalls out there, because we only saw ICMP unreachable messages where the packets were dropped only on 2% of all the paths. However, we saw nothing that would suggest you can't use a hop-by-hop option in a more controlled network, like data center networks, for example. And if we move on to the next slide. What does this all mean? All of these measurements mean for the minimum path MTU by hop option draft? Well, the packets that carry the option should be chosen quite carefully to avoid potentially throwing away important packets in a flow. So we want to advise setting this option on a probe packet rather than a packet in a flow. Then other aspects of the proposed option are those that apply to options in general. I mean, do we incur additional processing in the network, or do we potentially take away space from other options? But this is a very small option with a very small processing cost per packet. So this seems this does not seem like a concern. Another issue is the need for some on-path validation. So the information should be used more as a hint rather than something that directly drives a change. But I guess finally, a barrier to deployment of the hop-by-hop option is the fact that, of the minimum path MTU one, is the fact that the protocol stacks, this is not currently implemented. Protocol stacks don't currently have an API that can set or receive the information in a useful way. So if we go on to the last slide, I'm not entirely sure how I'm doing for time. I was meant to start a timer, but I didn't.
We're almost out, but this is a working group draft.
Huh.
So you can go a little longer.
Well, as you can see, we've had quite a lot of insights into options traversal with these probes, but we don't have nearly enough data from edge networks, and we would absolutely love to do more experiments. So I know an option for this would be RIPE Atlas, because there are many probes that are IPv6 enabled and in edge networks. So if you can help us run this kind of test on RIPE Atlas probes, that would be great. Because I don't think it's part of their normal suite of tests. But also, if anyone listening would like to host a probe or a virtual probe, I can give you basically a VM image, and you can deploy this in your data center. And please get in touch if you can do so. That would be great. Also, if you've done your own measurements and have some data to share, we'd absolutely love to hear from you. And that concludes my presentation. Hopefully, Gori is around here somewhere to help me answer any questions. Thank you very much.
Good. So stay on the audio. We'll have questions now. Okay, Eric?
Yeah. So first of all, Anna, thank you so much for this presentation. It's really a hot topic, and I fully support you up to the point of hosting a container, not a VM, though, in my edge network or in RIPE. My only concern in this study is that there is a heavy bias towards DNS server, which are typically hosted into big data center environments. Can you comment on this?
Yes, absolutely. We would love to also diversify the tests we do, which is why it's, I think the next big step would be to add TCP support in the software that we use to run the experiments, and do these towards web servers as well. I guess. Go on, sorry.
I just want to say, I would love as well to get a wall of shame of people dropping those legal IPv6 packets, so that it could be cool. Now, I do not think, honestly, that it's a public propose standards in 6-man rather than informational in V6 ops. But that's just a personal comment, of course. Good job again, right? Don't take me wrong.
Thank you very much. And for the wall of shame, I guess we can start with Comcast.
No comment.
A joke. We are working with Comcast to resolve this.
Yeah, people don't know there's a problem, then they can't fix it. Toilets.
Any more questions?
I was wondering about your API node. So I was just looking at. Unfortunately, I haven't played with it myself, but the Linux API says extension headers can be, received in receive message. So, or am I wrong on that? So I'm curious.
Oh no, sorry. I was talking about the PathMTU option specifically. There needs to be code to look at the option and to either modify it along the path or to
Just
extract
that one specific option. So there's no generic option. Okay, thank you.
Yes. Sorry, should have been more specific.
Okay. Anything else? If not, I think we can go to the next talk.
I guess, Bob, we should say that we plan to revise this document and bring it back to the working group and continue working on it. And we just got a release of the provisional assignment. Let us do that.
Okay, I think you were breaking up, but I think I heard you were planning to revise the document and bring it back to the working group.
Yeah.
Oli, I think Tom is on now, and I think he's next in the agenda. Yes, he is on. So, Tom, you have to request. There you go. Okay, Tom, go ahead.
Can you hear me?
Yes.
Great. So I'm going to talk about extension header attribution option. There is a draft on this that we recently updated. Next screen, please. So the motivation for this is that we want to be able to enable extension header insertion and removal in flight. This has obviously been a topic that has generated a lot of discussion in 6-man. First, it was, I guess, started by some of the needs for segment routing, but we're also finding that IOAM and QoS probably need this. The basic idea is that packets, as they ingress a limited domain, may be annotated with data, and that data would take the form of extension headers, typically hop-by-hop options, or segment routing header would be examples. And within the domain, they would be used as they transit it, and that at some egress point, we would want to remove the inserted options with the idea that the extension headers really need to be constrained to the limited domain, and we don't want to expose these outside of that. As we know, extension headers, for instance, on the internet, are not extremely reliable at this point. I think there's a few examples of this, as I mentioned. For hop-by-hop options, IOAM is being defined and would be quite useful for an operator to, as they measure packets transiting their domain. There's also a new initiative called network tokens. This is very similar to something that I had done called FAST. The idea there is we want to use hop-by-hop options to indicate QoS for packets. As I mentioned, segment routing was kind of the poster child use case of this. And in addition to segment routing headers, that would also kind of imply that we'd want destination options before the routing header. So those are probably the three types of extension headers that are most applicable here. I don't think that fragmentation or IPsec security would be applicable. Next slide, please. So I'll just do a quick overview of the problems that we've identified with extension header insertion, and then try to show how we're going to address those, or at least mitigate them. So fundamentally, this breaks the attribution model of IP, where in IPv6, the contents of the packet are attributed to the source node unless otherwise noted. And the only exception to this really is modifiable extension headers. For instance, hop-by-hop options that are marked as being modifiable in flight. The source basically indicates that the network is allowed to change that data. But anything outside of that, the network is not supposed to change per RFC 8200, as we know. And in particular, extension header insertion removal is not allowed for that reason. The other problem that we have is, and we saw this with segment routing, there's no way to know which headers were inserted. If we just insert a hop-by-hop option, for instance, and we want to remove it, we wouldn't know for certain whether that was actually created by the source or inserted by the network. So there's an ambiguity there that we'd have to resolve. It breaks PathMQ discovery, in particular for inserting new data into the packet that increases the packet size, and that runs the risk of packet loss later on in the stream where we exceed an MTU. It breaks ICMP in the sense that if we send an ICMP error on the basis of the inserted data back to the host, the source host again has no idea about this data. It did not create the packet, so therefore it can't really respond to the ICMP error in a meaningful way. Another issue is there's no feedback when a node inserts data headers and it causes downstream drops. And it also breaks AH in the sense that if there's inserted data and AH does a computation over that data, it will obviously fail in the computation. Next slide, please. So often when this topic is brought up, IP encapsulation is the suggested alternative. In fact, I think in the early versions of drafts of RFC 8200, this was actually mentioned as being the kind of the official alternative. There are some problems with this. First of all, this requires that we set a destination address to the decapsulating device when the for a device encapsulates. In a lot of instances, that might not be known. In segment routing, it's kind of implicit because the source is actually doing source routing, so it would know what the final destination address is. But for instance, in the IOM case, where we're just taking packets with data to do telemetry, there's no reason to believe that the source would always know the proper destination or the egress address from the network. Consistent routing, ECMP, may be required. So there's a big difference in how the ECMP hash calculation would work. If we're inserting headers, this really doesn't change any of the fields in the packet that we use for ECMP hash calculation. On the other hand, IP encapsulation fundamentally changes it. So packets that have extension headers inserted take a very different route than those that are using IP encapsulation to try to accomplish the same effect. And then lastly, there's more overhead when we're doing header insertion. In the worst case scenario, it's 40 bytes of IPv6 header. Next slide, please. So we defined an attribution option. The goal here is to satisfy these or address the requirements and the mitigations. It can be a destination or hop-by-hop option, but it does two things. Unambiguously identifies what extension headers or options were inserted into a packet, and it attributes that inserted data to the node responsible. So this is a standard option. So it has normal option type, option data length. It has 3 fields. So the E field indicates that an extension header has been inserted when it's set, and that follows. And then num-ops indicates how many options have been inserted into the header. And the identifying information or identification identifies the node responsible for inserting the data. The identification can be considered local. So in some cases, that could be an IPv6 address, or it could be some local identifier if we want to minimize the space in the hop-by-hop option. Next slide, please. The insertion operation, if there's no destination or hop-by-hop option, we will insert one and then insert the options following that. If there are already existing appropriate extension header, we will insert into that header the option. And there's 2 possibilities here. One is we're inserting options, and those could either be hop-by-hop or destination options before the routing header, in which case this would apply. The second case is when we're inserting an extension header. And for that, the idea is that we always precede inserted extension headers by a destination option that has the EBIT set. And that destination option could include other inserted options. So we can have actually one option could represent both inserted extension headers and inserted options. Next slide, please. Removal.
You are just about out of time. So if you could wrap up to allow a little time for questions.
Okay. Removal operation, it's a pop model, so we remove options in the reverse order that they were inserted. And the other thing that we can do is modify AH implementations to logically remove inserted data before computation, so that's not an issue. With that, I will end here.
Good. Any comments? Okay, don't.
So I posted the draft upstream, the latest version. It would be great to see comments, and I am intending at some point to ask for working group adoption.
Okay, Eric Klein.
Yeah, I had a question, Tom. The assertion that inserting headers doesn't change the ECMP processing kind of relies upon the fact that anything that's trying to do ECMP would continue to look past them for its like ECMP load balancing information, like trying to find a UDP header or something like that, right?
Well, it does if that's the way ECMP works. If it's using the IPv6 flow label, then it would only be the source, destination, and flow label. So that would work without requiring DPI. If the devices are doing DPI, which obviously many of them do, that would depend on they have the capability to parse over the hop-by-hop option extension header. If they're not doing that, then they're kind of breaking IPv6 anyway.
Well, but there's no guarantee that header insertion will not alter the ECMP behavior of some
devices. It is if the ECMP processing is correct, because say for instance hop-by-hop options inserted, as long as the devices parse over the hop-by-hop option, they can still extract the transport ports, and they still have the IPv6 addresses. So we're not changing any of the fields that are commonly used in ECMP to compute the ECMP hash.
Correct, but it might be inserting too much information, right? So that it's not possible for a device to read past whatever its buffer size was.
Okay, so this is a separate problem that I think is coming up also. This is the so-called parsing buffer problem. But I would point out that since this is in a limited domain, presumably the admin would address all of these issues. So that it's a controlled domain, so they can ensure that.
Okay, we're going to need to finish this on the list at this point. So thank you.
Okay, thank you.
To the next talk.
Okay, can you hear me?
We can.
Great. Okay. Hello. I am going to present this beer in 6 draft on behalf of co-authors from ZTE, Juniper, Cisco, Nokia, and FutureWave. Next slide, please.
And if you can also try to do this in less than the allocated time, it'd be good. We are running over.
Yeah, I'll try. Yeah. So BEER means bit index explicit replication. It's a new technology that achieves efficient multicast distribution without requiring per flow state in the network. The way it works is that the BEER multicast packet carries a BEER header in which there is a bit string. Each bit position in the bit string identifies corresponds to an edge router. So if a bit is set, it means that the corresponding edge router will want to receive the traffic. So the BEER forwarding router in the network, when it gets the BEER packet, it examines the bit string and decides which next hop BFRs you need to forward to. When it does that, it modifies the outgoing bit string because each next hop BFR will be responsible for only a subset of the incoming bit string bits. So RFC 8279 talks about the architecture for BEER. It has 3 layers. The multicast flow overlay that basically helps determine which bits needs to be set, and the BEER layer that does the forwarding, and the routing underlay basically provides a path to reach to the next hop BFRs. Next slide, please. I'm going to skip the details of BEER header. The key is that there is a bit string and other information in the BEER header. Now, let's move on to the next slide to see how BEER could be implemented in an IPv6 only network. In this network, I have routers A, B, C, D, E, F. Router A gets a multicast packet, and it needs to forward to edge routers D, F, and E. And from the multicast flow overlay, it determines that D, F, E needs to receive the traffic. So it sets 3 bits in those in the bit string. It puts on that BEER header, and now it needs to put on a next header, an outer header. So A and B are directly connected, so it could just put on an Ethernet header there. When B gets it, it replicates traffic to C and E because from the bit string, it knows that it needs to send the packet to C and E. So when it sends to C, it could just put on a Ethernet header, but when it sends to E, for whatever reason, it could decide that it's going to put on an IPv6 header before the Ethernet header. It does not matter what the outer header you use after the BEER header. It could be IPv6 header, it could be either header, or it could be anything that somehow makes sense. Next slide, please. So in this picture, there is a slight difference there. Here, the router B is incapable of doing BEER. So the router A needs to tunnel the packet to C. Now, being an IPv6 network, it's most natural to use the IPv6 header after the BEER header. But again, it does not really matter. Somehow the A says that I want to use GRE, is insert GRE header between the IPv6 and the BEER header. That's also fine. And so basically, to BEER, IPv6 is just outer encaps, and to IPv6, BEER is just a next header. Next slide, please. So in summary, IPv6 and BEER are orthogonal to each other. To IPv6, BEER is just next header, like any other payload. And to BEER, IPv6 is just outer header, like any other outer encapsulation header, BEER, either GRE, whatever. So what we need here is basically a code point to say that next header is BEER. And that is consistent with general BEER architecture and consistent with the general IPv6 IP architecture. So the draft has some details on how the IPv6 header is constructed when we do use IPv6 header, and I think we can skip those details here. So next slide, please.
So at this point, thank you. Why don't we see if there's any comments?
Yeah.
Eric?
Yeah, I was just wondering, because it's not really an extension header that you are requesting here. It's more like a transport header. So I'm not sure whether 6-man is the right working group to request this, or maybe I'm missing some points.
Oh, I'm sorry, I didn't make this clear. So the intended home for this draft would be the beer working group, but because it involves IPv6 network, we want to present it here to get people's comment here. And also there are other proposals to do beer in IPv6, and this is one way to do it.
Okay, my point was there, we may want to involve as well transport and inter-area on this, because it's not really an extension header per se.
It is not an extension header. Beer is just a payload on IPv6 in this proposal.
Okay, let's talk later.
Okay, Torles?
Yeah, I think if the answer was this is just informational and the people here in 6-man interested in that should go to the beer working group. Otherwise, if the engagement of the 6-man working group would be different from that, I'd like to understand that better.
And Jin Grung?
My comment is that there is no difference of IPv6 next header point and the IPv4 protocol code point.
You are correct. So I made a mistake in the preparing the slides, but I noticed that, and in the presentation, I didn't say IPv6 code point. Yeah. But you are correct. It is the same.
Okay, good. We can continue this on the mailing list. So next presentation.
Thank you.
Can you hear me?
Yes, go ahead. And if you could do this in 5 minutes, it would be very appreciated.
Okay, I will be quick. So this talk, I will talk about carrying VTN ID in the IPv6 extension header. I will present on behalf of the co-authors. Next slide, please. Over here, some background of this. The VTN concept is introduced in draft IETF's enhanced VPN, and as shown in the figure on the right side, basically VTN is considered as a virtual underlay network, which topology and the network resources required by a set of services, which is called VPN Plus service. Service is provided based on the combination of the overlay VPNs and the VTN as the underlay. So in order to make sure the service is processed appropriately in the network, the information of this associated with VTN needs to be carried in the data packet, so that on each hop, the node can steer the packet to the set of resources allocated to VTN for the packet processing. So in this document, we propose to carry this VTN identifier in the IPv6 extension headers so that it can be used for IPv6 network and also can be used for the SRv6 network. Next slide.
A question from Joel here. Do you want to take that in between?
Sure. Joel, go ahead.
I finished or?
So this draft assumes that a new extension, that an identifier in the packet for the VTN is needed, and then marches off to try to figure out how to create one and uses it for forwarding in ways that seem prone to loops. But before one gets to the problems with the details of the solution, I question the premise. It is not at all obvious, even if one wants to do binding to resources, which I grant one wants to do, that what one needs is a new forwarding sensitive identifier processed in the network in the packet.
Okay, I think I got a question. But can we finish this presentation first, because I have only a few minutes left?
Yes, go ahead.
Okay, thank you. Basically, in this draft, we define a new IPv6 extension header option to carry this VTN ID. The format is shown in this figure, and it can be skipped when unrecognized, and it cannot be changed in the path. And the VTN ID is 4 octet length to match the length of the network slice identifier in the wireless networks. Because we need this VTN ID be processed on each hop along the path, so it is recommended to carry this VTN option in the extension headers, which can be processed hop by hop in the forwarding plane or data plane. Next slide. So here are the procedures. First, the VTN ID option is inserted on the ingress node of the IPv6 or ISRv6 domain as an option in the outer IPv6 header based on some traffic classification or mapping policy of the operator. And along the path, the nodes which can pass this VTN option should use this VTN ID to identify the VTN the packet belongs to and use the local resources allocated to the VTN for packet processing. So in this case, the forwarding behavior can be based on both the destination IP and the VTN ID. If the node cannot pass this option, it should ignore this option and forward the packet just based on the destination IP address. Okay, next slide. Okay, we also have some deployment considerations added in this document. This is to take the implementations of the hop by hop option header into consideration. Basically, as specified in this.
If I can interrupt, I think we're going to need to wrap this up, but I think it would be good if you would address Joel's comment, because it's not the question of how you do it, it's a question of should you do it.
I guess Joe has a question about why we need a VTN ID to use for the packet forwarding, right? I think I already replied to his email in the mail list. We think this VTN ID has a different functionality as the DSCP, which has been used to differentiate traffic classes and priorities. The VTN ID is another kind of identifier to identify the virtual networks, and they don't have a priority between each other. We first identify the VTN, virtual transport network, then we can use the DSCP within the VTN. So this is a different concepts, and they have different functionalities. We think this can be used to provide guaranteed performance for some services which are required by some customers or services.
Okay, thank you. We're going to have to end now to leave a little time for the other talk, so we can continue this on the mailing list.
Okay, thank you.
Okay, Lee. Go ahead. Jiang Li, you should have audio now.
Hello, everyone. This draft proposes a solution. Oh, next slide, please. On a not well-managed network, no IP list available. So how can we know which IP address have been used? On IPv6, IP scan is effective, but on IPv4, IP scan is effective, but on IPv6 mission impossible. So this draft proposes a solution. Next slide, please. First step, set up a collection point. Second step, append the collection point address to the router advertisement so that this information can be flooded to network nodes. Router advertisement should be extended. Type is set to 39. We define 39 the connection point option type. Also set the IPv6 address of collection point. When a router receives router advertisement and finds that there is a collection point address, the router needs to record collection point address, and when next time the router sends router advertisement, collection point address should be attached. In this way, collection point address is flooded to the network. And at the same time, the router delays a random time, send a message to collection point to tell that this node is online. And when a host receives router advertisement and finds that there is collection point address, the host also delays a random time, and then a message should be sent to collection point. The third step is that when the collection point receives messages from hosts and routers, it should get the source address of this message and record addresses with timestamp. Finally, collection point get a list of online IPv6 nodes. By using timestamp, online address list can be updated. So this is the solution the draft proposed. Next slide. Scenarios of this solution, when used alone, it can do unintended IPv6 host discovery, or get IPv6 host list, do further IP scan and vulnerability scan, hosts and vulnerability management, or IPv6 network audit. This solution can be used in combination. For example, YAML model for reporting structured data, or protocols for network config, like netconf. So this is all about this solution.
Okay, I think that's the last slide. Yes, so thank you. We're about out of time, so I think we can defer any more discussion on this to the mailing list. So thank you. So that wraps up today's second 6-man session. Thank you all very much. I think it's almost the end of the IETF week. And I suspect we're going to get to do this again in November, but who can tell? Maybe someday we'll get to meet face to face again, but I doubt it's going to be this year. So Oli and I thank you very much, and we'll see you on the internet. For real. Thank you. Bye.